Okay, so for a square matrix, we haven't, we can do this with situations where you don't have a square matrix. But for a square matrix, this matrix product equals 0 if you have a non-trivial solution. It means that the columns of A are not linearly independent. If the only possible solution is the trivial solution, where all the C's are equal to 0, then the columns of A are linearly independent. Well, everything we said over here for this 3 by 3 case applies here. Because I can say this, okay, well, if the determinant of this matrix is non-zero, and I should say determinant of A is non-zero, but we understand that that's what we're doing. I guess I can kind of sneak in an A there. If the determinant of A is not equal to 0, then what can we say? Well, one thing we can say is that A has to reduce to the identity. We just explained in terms of 3 by 3s why that is. It's true for any dimension, because everything that I said here in arguing that the determinant's non-zero if A reduces to the identity is equally valid no matter how big your square matrix is, and you want to be sure you convince yourself of that. Okay? Now, other ways to say that: determinant A is not zero is equivalent to saying A reduces to I. Determinant of A not zero is equivalent to saying A is non-singular. That's exactly the definition of non-singular. And that should lead you to the idea that A is invertible, which is the easy way to have proven our original result. Okay? And then if A is invertible, well, that's equivalent to saying that the equation AX equals B has a unique solution, and also that AX equals 0 has only the trivial solution. Okay? All these statements are equivalent to saying determinant of A is non-zero. Every statement is true if and only if this is true, and this is true if and only if any one of these statements is true. And of course, if any one of these statements is true, they're all true. Okay? So we could have proven our result. Our result being that the columns of A are linearly independent if and only if this equation has only the trivial solution, all C's equal to 0. That's the statement. And if I have room, I probably should write that out. Don't really have room to write it out very well. I'm going to leave it unwritten because here's the basic equation. Okay, I'm saying again. Well, I could write among these conditions the thing that we're trying to prove, okay, which is the columns of A are linearly independent. Okay? Now, how do we establish this? Okay, how do we establish that AX equals 0 has only the trivial solution? Well, the equation is A times this column equals a 0 vector. If determinant of A is non-zero, A is invertible. If A is invertible, then this equation can be written, well, you take A inverse times both sides, you get C1 through Cn equals A inverse times your 0 vector. Well, any matrix times a 0 vector gives you the 0 vector, so that means that C1 through Cn is the 0 vector, so that C1 through Cn are all 0. Okay? So what we've established is if the determinant of A is not 0, then all the columns are linearly independent. And we've done that in just a couple of steps without having to go through all the details of these arguments, which are nevertheless very important to understand. Okay, so the elegant solution here is to say, well, this matrix equation holds. This matrix equation has only the trivial solution, if and only if determinant of A is non-zero, meaning then that the columns of A are linearly independent. Okay, that's where we've gone. If, on the other hand, determinant of A is 0, then there exists a non-trivial solution because the matrix is going to reduce to a row of zeros, giving you a free variable, giving you non-trivial solutions.